right, so welcome to my presentation for the SOAFEE 2022 symposium. My name is Jakub Sosnovec. I'm a software engineer at NXP. In particular, I work in the automotive processing business line. And this presentation is titled P3com, Not Another Middleware. So let's just jump in. To begin, I would like to give some motivation and context to these efforts and talk about the challenges that we are facing on the BlueBox 3 development platform. Next, I want to talk maybe in general about the various choices and options that are currently available in the middleware space. And this will then sort of bring me to the whole idea of p3com, our project, and its real-time version, p3com RT. So I want to talk about both the sort of concept of it, as well as some details of how it works under the hood. And to close this off, I want to discuss how we aim to integrate this into the whole SDV ecosystem. So the BlueBox 3 platform, it's development platform which I think is really ideal for software-defined vehicle experimentation, prototyping, development. It incorporates two independent processors, so the SO2G gateway or networking processor and the Layerscape LX2 high-performance processor. So on the right here, this is a part of the block diagram of BlueBox 3, and you can see the SO2G here on the left and the LX2 here on the right. And it turns out there is a PCI Express bus connecting the application cores on these two processors. Now, this is a fairly unusual setup for PCI Express, where usually it's used for with connecting a CPU with a passive device like a GPU. But in this particular case, it's really connecting these two completely independent devices, and but it has a really high throughput. And so the challenge here then is to come up with a convenient high-level mechanism or API to communicate and share data across this PCI bus between the SO2G and Layerscape devices. And additionally, if you look just inside the SO2G processor, there's the application core cluster, as well as a real-time unit consisting of 3 M7 cores. And typically, you might be running a real-time operating system there, such as FreeRTOS. And actually, there is an SRAM memory region, which is accessible by both the application cores as well as the real-time unit. So both applications running on Linux, as well as some safety application maybe running on the M7 cores. And again, the challenge then would be to come up with a way to share data over this SRAM memory between these two sort of very different worlds, and it should be somewhat symmetrical, consistent between the Linux side and the FreeRTOS side, but also high level enough to enable software-defined vehicle applications running on top of this API. So now these kind of problems are the domain of middleware typically, and actually there is already a really wide selection of middleware options that are available, both open source and commercial proprietary. And so if you just sort of briefly look at all the logos here, there is the DDS world with Rust2 running on top, and open source projects such as Cyclone DDS or FastDDS, as well as commercial ones. And then there is maybe some competition from AUTOSAR with its some IP protocol and things like this. And the whole idea that I wanted to demonstrate here is that there is such a wide selection already that we decided that we don't want to develop yet another middleware option and compete with all the existing ones. Rather, what we decided to do is to develop just a component with a limited scope that is then supposed to be integrated into a full-featured middleware just to accelerate communication and data sharing over the platform-specific interfaces, such as PCI Express or this data sharing over SRAM memory. And this idea is really nothing new. For example, already Cyclone DTS, it has an optimization for the inter-process communication case. So if you look at the picture here, in Cyclone DDS, if you have a publisher on one device and a matching subscriber on another device, it would by default use maybe a UDP over IP to get the data from device A to device B. But if you have a matching subscriber on the same device, Cyclone DDS is actually able to avoid the overhead of the networking stack and rather use a shared memory mechanism to share data more fast between the processes. And actually, in the case of Cyclone DDS, it's using another Eclipse project called Isorix to achieve this shared memory communication. So Isorix is really it's also a middleware library, but it only works for inter-process communication, but it's very, very good at that. It's really fast, minimum overhead. It then allows zero copy sharing. It's really very efficient, and we are quite fond of it. And for this reason, we actually found Isorix to be the perfect foundation for our project called p3com. And so p3com is an extension of Isorix, which enables it to work not just over shared memory, like it does by default, but also over additional platform-specific interfaces, such as PCI Express, CAN, this IPCF, which is a kind of a low-level NXP library for communication over shared memory, such as the SRAM case that I showed for BlueBox, and actually it has a sort of transport layer architecture that enables it to plug in additional transport layers and really easily add new platform-specific interfaces into p3com. So it's portable. For now we support Linux. Basically, we support any operating system that Isorix supports, and we also added a kind of custom support for FreeRTOS as, let's say, the default real-time operating system. But it should be fairly easy to port it to a different real-time operating system. It's pluggable because of the transport layer architecture, which I talked about. That there's a sort of clear small API that needs to be implemented to add a new transport layer, which is then just a kind of thin layer on top of maybe the driver. Like in the case of PCI Express, the transport layer is really just a small layer on top of the PCI Express driver. And for now, p3com is using publish subscribe communication model, but it's fairly easy to also build a service-oriented architecture model on top of it. Now, how it works under the hood is it's implemented as a sort of gateway daemon process running in the background. So this daemon needs to be running on every device that's involved in the communication. And it's listening to the shared memory Isorix communication or traffic that's happening on each device, and is forwarding this traffic across the specific transport layers to the other devices. And it actually has a kind of custom dynamic discovery mechanism to make sure that there is no redundant data copying or message sending. Now, this is very useful because it's completely transparent for the user. The user can just keep using the usual Isorix API, and maybe with a library on top of Isorix, such as Cyclone DDS, and they just need to make sure that this daemon is running, this gateway daemon is running in the background, and it will then automatically start using the transport layers added into the gateway daemon, and so this really enables a completely standard API usage, no changes required on the application side. It's very easy to add new transport layers again, as I already mentioned. In particular, the PCI transport layer is something that we are quite proud of, because there is a really kind of seamless, mature DMA integration, really enabling it to use the full throughput of the PCI bus, while also really keeping the very high level publish, subscribe, or service-oriented API of ISORIX or DDS. And this IPCF library, I already mentioned, this is an NXP library that we use for communication over the SRAM memory in SSD, but it can really work over any shared memory that's shared between multiple core clusters or just cores. So if you look at the stack, p3com consists of a custom fork of ISORIX, and then the gateway application itself, and all the individual transport layers, which then plug into the gateway application. Now p3com RT, it's the real-time version, and to achieve that, we actually had to come up with a custom port of ISORIX itself to FreeRTOS, because by default, ISORIX only supports Linux, Mac OS, and Windows. And the device we are really targeting here is these high-performance real-time processors, such as the SDV device, which you can see the block diagram on the bottom here. It has actually 2 real-time units, each with 4 R52 cores. And as in the case of SDV, there is an SRAM memory available, which can be accessed by all the cores in the system. In this case, it has 19 megabytes. So again, the idea here is to use this SRAM memory for data exchange and data sharing and synchronization between the individual real-time units, as well as cores inside the real-time units. And our intention here is to actually contribute the FreeRTOS port of ISORIX to upstream ISORIX GitHub. Okay, and finally, so it's clear that the performance of middleware is very critical for software-defined vehicle applications, while there is a great need for high-level APIs such as ARACOM, DDS, or ROS2, but also there is the need to sort of take full use of the hardware platforms that the applications are running on. And so we think that this p3com project really makes sense for this need. And yeah, so it really fits into the kind of the edge part of the SOAFEE framework. Yeah, so p3com, the advantage of it is that the public API of it is simply the ISORIX API. And so there is already a fair number of existing middleware integrations of ISORIX, and which then enables us to really integrate super easily into all of these, because basically you only need to run our gateway process daemon in the background. So there is the Cyclone TDS, which I talked extensively already. There is the eCal project, which was originally from Continental, but also recently contributed to Eclipse Foundation. And then there is, for example, the Cook-Saval project, which is kind of a custom vehicle signal specification implementation. And okay, maybe a final note is that I so recently noticed that Apex AI joined the SOAFEE group, and actually because Apex AI are actually based on top of Cyclone DDS and ROS2, I think there's also a very good potential for integration there. So this is something that could be explored. And with this, I would like to thank you for listening and close this presentation.